I would like to introduce our first presenter for the Innovations in Railway Engineering technical session. Our first presenter is Dr. Pariza Haji Abdolraza, who is a postdoctoral fellow at the Canadian Rail Research Laboratory. She's led field instrumentation and monitoring campaigns and currently leads a research project on quantifying soft subgrade by BTD and IWS measurement systems. She's well known for promoting Canadian design and construction technologies for buried soil steel structures in the Middle East and has published a book and more than 20 articles in this field. Please join me in welcoming Pariza.
Hello, everyone. Hi everyone. Thank you for making some time to join my presentation today. I will be presenting about evaluating the ride quality and rail surface roughness from mounted accelerometers on in-service passenger rail cars, which is part of as an extensive research with the objectives of first to evaluate the effect of track geometry and track features on the passenger's ride experience using onboard accelerometers, and second, to develop a method of interpreting acceleration measurements to provide a measure of track geometry conditions, and thus a means of monitoring track geometry from in-service rail cars. And all this research was about how we analyze the vibrations collected by accelerometers. Our everyday life is full of vibrations. Our children enjoy the adventure of walking on a suspension bridge or riding a swing. But when these vibrations are mixed, get random at different directions, they make us motion sickness. This is something we definitely don't want to experience when riding a train, or we don't want to have a coffee spill on us. For this reason, the National Research Council Automotive and Surface Transportation Research Center, in collaboration with the Via Rail Canada, instrumented a Via Rail coach car. The accelerometers were installed under the car body and also on trucks and axle box, access bolts of the wheels. We only analyzed the car body and axle box measurements for this research. 7 accelerometers were mounted on the body of the car and 3 on each of 4 axle boxes. The instrumented car was operated in revenue service train with passengers on board, and data were collected between February and August of 2018 under actual operating conditions. The surface track geometry data were recorded by track geometry inspection car on July 15, which was very close to one of our measurements with rail car. Figure 2 shows the original vertical, lateral, and longitudinal acceleration data recorded, as well as the train speed during the data collected on July 2018. The data shows the train predominantly operated at a speed greater than 100 km per hour. The stops at 2 intermediate stations are identified from very low speed and accelerations values in figure 2A and B. Figure 2B represents the original vertical axle box accelerations recorded from left and right side of the train. Figure 2C presents the track surface and alignment and the corresponding curvature of the track recorded on July 15 by the track geometry car. Car body and axle box accelerations were collected at the frequencies of 500 and 5000 Hertz respectively. The geometry data were recorded at 0.3 meter intervals. The alignment of acceleration and geometry data was carried out by correcting GPS coordinates and accounting for their phase shift and distance lag. According to ISO 2631 standard, ride quality is the level of vibrations felt by passengers. In this research, I first calculated the combination of weighted accelerations in 3 directions, which is defined as AV or running RMS. The ISO classification for RQI is tabulated in Table 1. A little uncomfortable in this paper refers to ride quality value between 0.315 and say 0.5 meter per square second, and fairly uncomfortable refers to ride quality value greater than 0.5 meter per square second. Figure 4 shows that mainly at the location of track features such as grade crossings and bridges, fairly uncomfortable vibrations are measured. The assessment of vibration of ride quality values in figure 4 indicated that some locations had recurring spikes of our RQ values. For example, for the grade crossing record located at 29 and also 43 kilometer from the origin station, the ride quality value on March 2023 of 2018 was within a little uncomfortable range, while for later dates exceed to fairly uncomfortable. Based on August 2018's results, the ride quality values are plotted as color map for a study track to indicate the locations of track where the assets might need upgrade to improve the ride quality and to maintain the current operating speed. Our second objective of research was to develop a method of interpreting acceleration measurements from the instrumented Vias passenger rail car to quantify track surface geometry conditions. So first of all, track geometry condition is an important measure to ensure the safe operation of rail lines. One measure to this is surface roughness. Surface roughness means where vertical alignment of track are deviated from their designed position. Using the Gaussian filter, which is a computational metrology method, I developed a new technique which evaluates surface roughness from accelerometers. Based on the Gaussian filter metrology, track profile has different wave components. Waviness, which is attributed to a stiffness and long wave geometry variations, and short wave roughness, which are attributed to rail surface corrugations. To calculate relative rail displacements from axle box accelerations, I double integrated the relative displacements to calculate rail surface displacements. There are many details to eliminate the nonlinear trends and applying baseline corrections. And if you're interested, the details can be found in our 2 recent publications listed in the references. Figure 7b and c shows part of the results of velocity and displacement using single and double integration after applying nonlinear deterrent and baseline corrections. I calculated the root mean square to compute rail surface roughness from relative displacement of rail surface, which are shown in black lines. And I also calculated the RMS for the measured rail surface by geometry inspection car, which are shown in red lines in figure 8 with a 10-meter window length and overlap ratio of 0.99. Different length of moving window and the overlap ratio has been tested to achieve the best relationship and to account for surface condition and sufficiently large statistical sample to be representative of a studied characteristic. The power spectral density, or PSD, is computed for the calculated and measured rare surface moving RMS in figure 9. PSD allows for comparing the spatial frequency and therefore the wavelength of the calculated and measured ray surface moving RMS, regardless of the speed of measurement by the train and the track geometry car. This figure shows that there is a significant peak for at about 0.17 and 0.40 of the spatial frequency, which are as a result of ray surface deviations with wavelength about 6 and 2.5 meter respectively, which they will match together. The result of this research in general showed that the right quality values along the railroads presented more recurring peaks at track features, mainly at bridges and grade crossing, which is like increase from March to August, the time frame that we have studied. These recurring observations might be in general related to degradation of ride quality from passing traffic, which is 3.5 mgt annually, but this needs more further study. The comparison between the moving RMS of calculated and the measured race surface along the length of the study track represented identical magnitudes and variations. And the results show that the applied computational metrology method is promising technique to calculate the rail surface roughness of track geometry from Excel box accelerations data. And these techniques make it possible to frequently assess the track geometry in terms of surface while the rail car is in revenue service. I would like to thank the National Research Council Canada for motivating this research, for sharing collected data, and for partial funding for the research. And I also gratefully acknowledge the collaboration of Via Rail Canada, particularly assistance provided by Paul Turbachi, and also acknowledge support of TransCanada and Canadian National Railways for supporting Carl. Here are the list of references and two of our recent publications where you can find more details to this research. Thank you very much for listening to this presentation, and I would be very happy to answer any questions.
Perfect. Thank you a lot, Parisa, for a great presentation and all your great work this weekend on the conference.
Thank you. My pleasure.